So I want you to picture this. Your finger is just kind of hovering right over the enter key.
Right, the classic digital hesitation.
Exactly, yeah. You're staring at your screen, and you're caught in what is, well, fundamentally, a high-stakes digital standoff.
A Mexican standoff, but with data.
Yes,
Okay.
exactly. So think about a situation where you need to send a highly sensitive, an incredibly valuable file to someone.
Like a trade secret or something.
Right. This could be a proprietary design schematic for a new piece of hardware, or maybe it's a confidential legal settlement. It could even be a highly sensitive medical database.
Oh, wow, yeah. High stakes.
Very high stakes. But there's just one massive catch here. You do not entirely trust the person on the other end of the connection.
Which, let's be honest, is most of the internet.
Right. And they need to send an equally sensitive, equally valuable file back to you.
So it's the ultimate bottleneck, really, in digital communication.
It really is. So there you are, both of you. Who actually hits send first?
Right, because someone has to go first.
Exactly. And if you, the listener, go first, they might just, download your proprietary file, say you a quick thanks, and completely ghost you.
Yeah, and then you're left holding nothing but a sent receipt, and your data is just gone.
Gone, but, if they go first, well, you could technically do the exact same thing to them. So how do you resolve that?
It's a huge problem.
Right, like how do you exchange valuable digital assets without someone getting burned and without having to just blindly trust the other person?
Well, historically, the digital world has basically just relied on blind faith for peer-to-peer exchanges, which is, it's a terrible security strategy.
Yeah, hope is not a strategy.
Exactly. Or, alternatively, it relies on this massive, heavy legal framework that operates, off-screen. The threat of getting sued is often the only thing actually enforcing the trade.
Right, the lawyers are the backup plan.
Right, but in a globalized digital ecosystem where you might be trading with some completely anonymous entity across the world, those legal threats are totally hollow. You can't sue someone if you don't know who or where they are.
Which brings us to the mission of today's deep dive. We are unpacking a solution to this exact standoff. And it's one that doesn't rely on lawsuits, and it definitely doesn't rely on blind faith.
No, it relies on math.
Pure math. We're looking at a deeply technical, highly ambitious academic paper from the year 2026. It was published in the ISIS Journal of Information Systems.
Yeah, and the title of the paper really gives you a hint at the kind of density we're dealing with today.
Oh yeah, read the title for us.
It's called Implementation and Analysis of a Synchronization Protocol for Fair Exchange with Strong Fairness and Privacy.
Yeah, that is a formidable title.
It's a formidable title for a truly formidable piece of engineering, honestly.
But the core of what we are talking about here, if we strip away the jargon, is a newly implemented protocol called FUWD. That's spelled FEWD.
Right. Fair exchange without disputes.
Fair exchange without disputes. It is a system designed to allow two completely untrusting parties to exchange digital goods with absolute mathematical fairness and perfect privacy.
And the real kicker, the thing that actually makes this revolutionary, is that it does all of this without relying on some giant centralized corporate middleman to oversee the trade.
Right. No big tech company acting as the referee.
Exactly. That is the massive paradigm shift here. The source material today is dense because it bridges, well, several distinct fields.
Yeah, it's not just a software paper.
No, it's pulling from theoretical computer science, advanced cryptography, and, real-world software engineering. These researchers didn't just write a philosophical treatise on how this might work in theory.
They actually built the thing.
They built it. They guide us through mathematical finite state machines, linear temporal logic formulas, all the way down to the actual Python code and Docker containers required to make the system function in reality.
So if you are listening to this and wondering if you need a PhD in computer science to follow along, do not worry.
We've got you covered.
We're going to keep the mechanics grounded. By the end of this deep dive, you are going to understand the underlying logic of this invisible architecture.
You'll see exactly how it works.
Right, and why it might very soon power everything from your everyday online purchases to massive, global medical data networks.
It's foundational stuff.
It is. But to understand the brilliance of the FUWD solution, we really have to thoroughly understand the trap that system architects have been stuck in for decades.
Yeah, the trust dilemma.
The trust dilemma.
Yeah.
Because we have been trying to solve this digital standoff for a very long time, haven't we?
Oh, decades. The formal academic term for your standoff scenario is a fair exchange protocol, or FE.
Okay, FEP?
Right.
Right.
And if we look at the timeline in the paper, serious research into this traces all the way back to the 1980s. It was heavily pioneered by researchers like Asicon in the late 90s.
So this is an old problem.
A very old problem. The theoretical goal was established early on. It's simply to ensure that when Alice and Bob trade digital items, either both of them receive what they want or neither of them does.
That sounds pretty straightforward.
It does. The core requirement is just that nobody walks away empty-handed while the other person gets the prize.
Right. That sounds like a simple binary outcome. Both win or both lose. But the paper draws a very sharp, almost painful distinction between two types of fairness.
Yes. Weak fairness and strong fairness.
Right. So where does the weak version fall short? Like, why is it weak?
Well, weak fairness is a protocol that it tries its best, but fundamentally it acknowledges that digital environments are chaotic.
Right. Wi-Fi drops, computers crash.
Exactly. It accepts that things can and will go wrong. Connections drop, power fails, or, more likely, one party actively behaves maliciously.
Right. Someone tries to pull the plug right at the crucial moment.
Yes. In a weak fairness protocol, if an interruption occurs right at that critical moment, one party might actually end up with an unfair advantage.
Wait, really? So they get both items and the other person gets nothing?
Yes, unfortunately.
But hold on, if someone gets cheated, how can it even be called fairness, even a weak one?
That's a great question. Because the protocol provides an evidentiary trail.
Oh, like a receipt?
Basically, yeah. It generates cryptographic receipts and logs of the transaction. The weak fairness protocol basically says, look, we failed to protect you in real time, but here is an undeniable, mathematically verifiable log proving that you were cheated.
Oh, wow. So you get ripped off, but at least you have proof you got ripped off.
Right. And then the cheated party takes that log to a human arbitrator. They go to a judge, a traditional court of law, or some dispute resolution center to get things rectified after the fact.
I see. So it is essentially kicking the can down the road to a human. The software just throws its hands up and says, let the lawyers figure it out.
Exactly. It relies entirely on human intervention, which, as we know, is slow, biased, expensive, and often geographically impossible if the two parties are in different jurisdictions.
Yeah, good luck suing someone in another country over a dropped internet connection.
Exactly. So strong fairness, on the other hand, that is the holy grail of distributed systems.
The Holy Grail.
It provides an absolute real-time guarantee. It ensures mathematically that upon the termination of the protocol, whether it finishes successfully or gets aborted halfway through, no one is at a disadvantage.
Ever.
Ever. You either successfully trade or the items remain locked with their original owners.
Meaning no human dispute is even possible. The math just prevents the cheat from occurring in the first place.
Right.
So, okay, obvious question here. Why hasn't everything on the internet just been built with strong fairness from day one? If it's the Holy Grail, why aren't we using it everywhere?
Well, because of a mathematical brick wall that was discovered in 1999.
A brick wall.
Yeah, two researchers, Paglia and Gartner, published a landmark impossibility proof.
An impossibility proof, meaning they proved it literally cannot be done.
Yes. They proved mathematically that achieving strong fairness is strictly impossible between two independent parties without the involvement of a trusted third party, a TTP.
Oh, wow.
Yeah. They demonstrated that fair exchange is at least as difficult as the classic computer science problem of distributed consensus.
Okay, hold on. Define distributed consensus for the listener. Because, I mean, if I am trying to trade a file with you, it feels like it is just the two of us. Why is consensus so hard?
Well, think about two independent computers trying to agree on a single shared reality at the exact same moment over an unpredictable network like the internet.
Okay.
Because messages take time to travel, right? And because either computer could crash at any millisecond, they can never be 100% certain of the other state.
Because there's lag.
Exactly. If my computer sends you a message saying, I am releasing my file, how do I know you received it before I actually release it? I need an acknowledgement from you.
Right, you need me to say, got it.
But how do you know I received your acknowledgement? You need an acknowledgement of my acknowledgement.
I see, it just goes back and forth forever.
It creates an infinite loop of uncertainty. Paglia and Gartner proved that the only way to break that loop and guarantee simultaneous state change is to introduce a referee, a central controller.
Wow. So the math of the universe essentially dictates that we must have a middleman to achieve fairness.
It's mathematically required, yes.
And in the real world today, that middleman is usually some giant centralized server, right? Like an escrow service or a massive digital payment platform.
Yes, exactly. The monolithic trusted third party. The architecture is straightforward. Both Alice and Bob send their items to this central server.
Right.
The central server holds both items, verifies that they match the agreed upon descriptions, and only when it has both items securely in its possession does it hand them over to the respective new owners.
Which solves the loop.
Yes, it breaks the consensus loop and guarantees fairness perfectly.
But wait a second. If both parties are sending their highly sensitive files to a central server, doesn't that server see everything?
Yes. Yes, it does.
Like, if I am trading confidential medical data or proprietary source code, I am now handing it over to a third party. I mean, using a traditional TTP is like hiring a referee to oversee a trade of highly secret diaries, but the referee insists on sitting down, reading both diaries cover to cover, and checking the handwriting before handing them over.
That is the exact paradox the paper highlights. That's the perfect analogy.
It seems like a huge flaw.
It is. The monolithic TTP solves the fairness problem, but in doing so, it creates a massive privacy loophole. The central server has to process the sensitive information in plain text to mediate the exchange.
Plain text, so it's not even encrypted while the server looks at it.
It can't be, because the server has to verify what the file is. So in a modern information system handling highly valuable data, that central server becomes a massive liability.
A honeypot.
Exactly. It becomes a honeypot for hackers. If you breach the TTP, you breach every single transaction flowing through it.
Wow. Okay, so let me just get this timeline straight. In 1999, Pagina proves mathematically that we absolutely must have a middleman for strong fairness.
Right.
But relying on a middleman fundamentally destroys the privacy of the data being exchanged.
Also right.
So how do you reconcile that? Aren't system architects just trapped?
Well, they were trapped. For decades, the industry just accepted this trade-off.
Really? They just dealt with it?
Yeah, you could either have peer-to-peer privacy, but risk getting ripped off, or you could have guaranteed fairness by giving up your privacy to a central corporate server.
That is a terrible choice to have to make.
It is, but the researchers behind the FUWD protocol realized something profound. They looked at Panya's mathematical proof, which says you need a TTP, and they realized they didn't have to get rid of the middleman to preserve privacy.
Okay.
They just had to chop the middleman up into pieces.
Chop the middleman into pieces. I mean, that is a visceral image.
It is, yeah.
What does a chopped up middleman actually look like in the architecture of this protocol?
So the paper introduces what they call a split TTP architecture.
Split TTP.
Right. Instead of one giant monolithic central server that handles the entire transaction, the FUWD protocol basically fractures the trust mechanism into three distinct, highly specialized components.
Okay, 3 pieces. What are they?
You have 2 attestables, one residing with Alice and one residing with Bob, and you have one public bulletin board, or PBB.
All right, let's dissect those pieces one by one, because this is where the paper really gets into the hardware. It mentions that these attestables are trusted execution environments, or Ts.
Yes, Ts.
What is a T doing that a normal computer processor cannot do?
A trusted execution environment is a secure, completely isolated enclave that exists right inside the physical hardware of a device's processor.
Inside the actual silicon?
Yes. The paper names the specific real-world technologies that power this today. Things like ARM Trust Zone, Intel SGX, AMD SEV, and Amazon Nitro enclaves.
Okay, I recognize some of those names.
Right, they are major industry standards. When you run a piece of code inside one of these Ts, it operates in complete isolation from the rest of the machine.
Complete isolation.
Complete. The main operating system, the other applications, and even the human owner of the device cannot look inside this enclave to see the data being processed, nor can they alter the execution of the code while it is running.
Okay, wait. Let me push back on that because it sounds counterintuitive.
Sure.
The middleman is living inside my laptop.
Yes.
If it is my laptop, I own the hardware. I own the processor. I own the RAM. If I am the malicious party, couldn't I just use a debugger or hack the kernel of my own operating system to peer inside that enclave and steal the other person's file?
You cannot. And that is the absolute brilliance of hardware-level isolation.
Really? Even if I own the machine?
Even if you own the machine, you have physical access, yes. But the T is protected by cryptographic keys that are burned into the silicon at the factory.
Oh, burned into the silicon.
Exactly. The memory used by the T is hardware encrypted. Even if you dump the RAM of your machine, all you will see is encrypted garbage. But the real magic of a T is a capability called attestation.
Attestation. How's that work?
Because the T has those factory-burned cryptographic keys, it can generate a digital signature proving exactly what code is running inside of it.
Oh, I see.
Right. It can cryptographically prove to an outside party like Bob that it is running the exact, unmodified, open-source FUWD protocol code and that the enclave hasn't been tampered with.
That's wild.
So Bob doesn't have to trust you, Alice. He doesn't have to trust your operating system or your firewall. He only has to trust the isolated, unhackable silicon vault inside your machine.
That is fascinating. It's almost like having an incorruptible digital notary public permanently welded to your motherboard.
That's a great way to put it, yes.
But wait, if these are specialized hardware enclaves, does this mean you have to buy like a $10,000 enterprise server just to make this trade?
Not at all, and that is why this 2026 paper is so incredibly timely. The proliferation of technologies like ARM Trust Zone means that these Ts are already in modern smartphones.
Wait, my phone has this.
Yes. Intel SGX and AMD SEV are in standard consumer laptops. Everyday users are walking around with military-grade, secure execution environments in their pockets right now.
Oh, wow.
So the hardware infrastructure for a massive decentralized trust network already exists. It's just sitting there waiting to be used.
Okay, so Alice has an unhackable vault on her device.
Mm.
Bob has an unhackable vault on his device. They can prove to each other that the vaults are secure. That covers two pieces of the chopped-up middleman.
Right.
What is the third piece? The public bulletin board.
Yes. The public bulletin board is the only part of the system that is shared between the two parties.
Okay. Where does it live?
It can be hosted on any public server.
Mm.
Conceptually, it could just be a basic web server or even a blockchain, though the paper uses a traditional database because it's much more efficient.
Got it.
Its only job is to act as a highly visible public ledger where Alice and Bob's enclaves can post simple messages and read messages.
All right, so we have our three pieces. Let's put them in motion.
Let's do it.
If I am sitting at my desk and I want to trade my proprietary CAD file for your legal document, how does the trade actually happen without either of us getting ripped off? Walk me through the steps.
Okay, so any fair exchange protocol, including FUWD, can be broken down into 4 fundamental operations: deposit, verify, synchronize, and release. Or sometimes release is called restore.
Deposit, verify, synchronize, release.
Well,
Got it.
let's walk through how FWD distributes these tasks across that split TTP architecture. But before the official operations begin, there is a preliminary phase called the handshake.
The handshake. This is where Alice and Bob agree on the terms of the trade.
Yes, they agree on the URL of the public bulletin board they will both use. They exchange TLS certificates to establish secure, encrypted communication channels directly between their two Ts.
So talking vault to vault.
Exactly, vault to vault. And most importantly, they agree on a precise mathematical description of the items they are trading.
Now, the paper gets incredibly specific here about how that item description works. It mentions concepts like setup values, doc values, and a gather function. It seems like they're going to great lengths to ensure there is zero ambiguity about what is inside the files being traded.
They have to, because remember, there is no human referee looking at the files.
Right, the system has to figure it out itself.
Exactly. The protocol needs a rigid mathematical way to say, yes, this file is exactly what was promised. So during the handshake, they define the setup values. These are the expected properties of the item.
Like what?
For a CAD file, it might be a specific cryptographic hash, a certain file size, or specific metadata tags.
Okay, so they agree on what the file should look like mathematically. Then what happens?
Then we move to the deposit and verify phases. And this is where the magic of the split TTP architecture really shines. Alice and Bob take their encrypted items and deposit them directly into each other's Ts over that secure TLS channel.
Wait, hold on. I'm depositing my file onto their machine before the trade even happens.
Into their T, not their general machine.
Right. Into the vault on their machine.
Exactly. Inside those isolated hardware vaults, the items are decrypted. Then, that gather function you mentioned kicks in.
Okay, what does that do?
The T's internal code looks at the actual plaintext file that was just deposited, extracts its properties into a list called doc values, and runs a verify function to compare those dark values against the setup values that they agreed upon during the handshake. If they match perfectly, the T's internal state registers the item as valid.
Okay, I think I need a metaphor here to just wrap my head around this.
Sure.
It is like we both send each other a locked, heavy-duty titanium safe containing our items. The safes are sitting in our respective living rooms.
Right.
We can look through a tiny bulletproof window in the safe, and that window is basically the vera function, to see that the item inside is genuinely what we asked for.
Yes.
I can see your legal document in my living room. You can see my CAD file in your living room. But neither of us has the key to actually open our respective safes yet.
That metaphor tracks perfectly.
Yeah.
And what you have just described really highlights the genius of the FUWD protocol's strict separation of duties.
The separation of duties meaning?
It separates document manipulation from synchronization. Everything we just talked about, the deposit, the decryption, the extraction of values, the verification, that is all document manipulation.
Right.
And all of it happens locally, strictly confined within those isolated T-safes. The sensitive data never leaves the local devices.
Wow.
The central server hasn't been involved at all yet.
Which completely solves the privacy flaw of the old monolithic middleman.
Yeah.
The referee never reads the diaries because the diaries never went to the referee.
Exactly.
But we still have a massive problem here. I have a locked safe in my living room. You have a locked safe in yours. We have verified the goods are inside. Who turns the key first?
Back to the standoff.
Right. It feels like we have just recreated the exact same digital standoff, just with fancier hardware on our local machines.
We have. But now we've reached the final two operations: synchronize and release. And this is exactly where the third piece of our split middleman, the public bulletin board, enters the picture.
Okay, let's hear it.
It solves the standoff, but it does so without ever looking at your data.
Let's really dig into this public bulletin board then, because the paper emphasizes that the PBB is stateless and application agnostic.
Right.
What do those terms actually mean in the context of this software architecture? Why does it matter that it's stateless?
Let's start with stateless. In a normal monolithic TTP, the central server has to remember the entire context of the trade.
Like who is trading what?
Right. It has to track who Alice is, who Bob is, what stage the trade is at, and it actually holds the files in its memory. A stateless server remembers absolutely none of that logic. It doesn't process any complex rules at all.
So it's kind of dumb.
Very dumb. And application agnostic means the PBB has absolutely no idea what kind of software is talking to it, what kind of enclaves are being used, or what is being traded.
So how did the researchers actually build it in their implementation if it's so simple?
They built the PBB using a very lightweight Flask RESTful API sitting on top of a standard PostgreSQL database. It is incredibly simple. It literally only accepts two types of commands.
Just two.
Just two. First, it accepts simple text strings, known as tokens, via a persister request. Second, it spits out a sequential log of those tokens when someone makes a retrieve request. That is the entirety of its function.
Just text strings. Give me an example. What is a T actually posting to this board?
It is posting a string as simple as synca or cancel B.
That's it.
That's it. During the handshake phase, Alice and Bob generated a unique random exchange ID. When Alice's vault has verified Bob's file and is ready to proceed, it sends a POSTIS request to the PBB under that specific exchange ID with the string synca.
Okay.
Bob's vault does the exact same thing, posting sync B.
Okay, let me make sure I'm visualizing this correctly. The PBB is essentially a public flagpole in a town square.
I like that, yeah.
My T runs up a green flag with synca on it. Your T runs up a green flag with sync B on it. We both take a step back. Our T's are constantly looking at the flagpole. The moment my T sees both green flags flying simultaneously on that pole, it automatically pops open the titanium safe in my living room, releasing your file to me.
Yeah.
And your T does the exact same thing at the exact same time.
Exactly.
And the flagpole itself has absolutely no idea what is in the safes or even who put the flags up.
Your analogy is spot on. But consider the structural implication of that flagpole. By using a public, stateless ledger to coordinate the timing, the FUWD protocol entirely sidesteps the privacy nightmare of the 1999 monolithic server.
Because it's just meaningless strings of text.
Right. The PBB guarantees fairness simply by maintaining a verifiable sequential timeline of these meaningless text strings. The hardware T's do the heavy lifting of watching the sequence.
I see.
Only when the T reads the log and sees both sync tokens will it execute the release operation. So you get absolute guaranteed fairness combined with absolute peer-to-peer privacy.
It is an incredibly elegant mechanism. It uses the radical transparency of the public flagpole to coordinate the dark, isolated vaults.
Very poetic, but yes.
But let me play the cynic for a moment here.
Please do.
What if someone attacks the flagpole? What if a malicious actor hits the PBB with a massive DDoS attack, taking the server offline right after I post my synca flag?
Ah, okay.
Or even simpler, what proprietary CAD file is still locked inside the enclave on his machine. I can't just leave it in limbo forever. Am I trapped waiting for a second flag that will never come?
This is a critical vulnerability in any distributed system, and it is something the researchers addressed with a property called strong timeliness.
Strong timeliness.
Yes, it is the protocol's built-in escape hatch. Strong timeliness is the mathematical guarantee that any participant can unilaterally and immediately cancel the protocol at any time without needing permission from the other party and without needing to wait for a response.
So you are never, ever trapped in a deadlock.
Never.
Okay, walk me through how that escape hatch functions practically. Because if I pull the ripcord and cancel, I need absolute mathematical certainty that my file, which is physically sitting in Bob's T safe, is going to be destroyed or permanently locked.
Yeah.
I cannot risk him getting it later.
The paper models this by breaking the transaction down into timelines, specifically defining safe intervals, risky intervals, and uncertain intervals.
Let's use my scenario.
Okay, let's take the exact scenario you described. Alice posts her Synca token to the PBB. She is ready to trade, but Bob vanishes. His computer drops offline.
Right.
Alice waits a few seconds, she retrieves the log from the PBB, and it only shows Synca. She has now entered a risky interval.
Because she is publicly committed to the trade, but Bob hasn't, so she is exposed.
Precisely, but because of strong timeliness, she has the power to close that exposure. The application running on her computer tells her T to initiate a cancellation.
Okay, what does the T do?
Her T generates a new token and posts it to the PBB, cancellate. Now, Alice performs another retrieve operation on the database. The log comes back, and it now reads, Synca, cancellate.
And what does Alice's T do when it reads its own cancel token back from the board?
The T operates on a finite state machine, a strict set of mathematical logical rules. When the FSM sees that cancel a token in the log, it immediately transitions into a permanent exchange-canceled state.
So it locks down.
It unlocks Alice's safe, returning her own file to her, and it permanently deletes Bob's file from its memory.
Okay, but what about my file on Bob's machine? That's the one I care about.
This is the crucial part. Bob's T is programmed with the exact same FSM logic. Whenever Bob finally comes back online, maybe an hour later, maybe a year later, and checks that same PBB log for that exchange ID, his T will see the cancel a token.
Oh.
His T will immediately lock down and transition to exchange canceled. It will purge Alice's file from its memory.
So he can't get it.
He can't. Even if Bob tries to quickly post a sync-B token, it doesn't matter. The cancellation token is already recorded in the sequential log. The trade is permanently aborted, and the items remain secure.
Hold on, let me introduce a race condition here. What if it is a literal photo finish?
Okay, let's hear it.
What if I decide to cancel and post-cancel, but at the exact millisecond my signal reaches the TBB, Bob's computer finally reconnects and posts his sync-B? We both hit the flagpole at the exact same moment.
Right.
Does one safe read the cancel and stay locked, while the other safe reads the sync and pops open? Because if that happens, strong fairness is completely broken.
That is impossible due to the nature of the database managing the PBB.
Why is it impossible?
The PBB is a sequential database in this implementation, PostgreSQL. Databases inherently serialize incoming requests. It is structurally impossible for two write events to be logged at the exact same database millisecond.
Ah, so someone has to be first.
Always. The
Yeah.
database engine will enforce a lock. It will process one POST request, commit it to the log, and then process the other.
Okay, so the log will either read synca, sync-B, cancel-A, or it will read synca, cancel-A, sync-B. There is literally no tie.
There are no ties in a serialized database. And because both of the isolated hardware vaults read their instructions from that exact same sequential log, they will both independently arrive at the exact same symmetrical conclusion.
So if sync-B got there first.
If sync-B landed in the database first, the FSM logic dictates that both safes open. If cancel-A landed first, the logic dictates that both safes lock down. There is zero ambiguity.
Wow.
The researchers note that while Alice might experience an uncertain interval while she waits to retrieve the final log to see which token landed first, the protocol guarantees that the final state will be identical for both parties.
The logic is incredibly tight. It sounds impenetrable. But I have to ask, how do we actually know there isn't some hidden loophole?
Sure, humans make mistakes.
Right. Anyone who has ever worked in software knows that you can write a program, you can think it's utterly bulletproof. And then on day one, some user clicks two buttons simultaneously while disconnecting from the Wi-Fi, and the whole system crashes.
The infamous edge cases.
Yeah, exactly. And if a corporation is using FUWD to trade a $100 million intellectual property file, a bug isn't just an inconvenience, it is catastrophic. How do the researchers prove that this theoretical perfection actually holds up in reality?
That skepticism is exactly what drives Section 6 of the paper, and it is arguably the most rigorous and fascinating part of their entire research.
Really? How so?
They didn't just write the Python code, run a few tests, and hope for the best. They proved the system mathematically using a technique called formal verification, specifically using a tool called the CEFME model checker.
Let's break down model checking because, in standard software development, programmers write unit tests. They write a script that says, if Alice inputs X, make sure the program outputs Y. Is model checking just a really massive suite of unit tests?
It is fundamentally different. It is an entirely different approach to software validation. A unit test only checks the specific scenarios that the human programmer thought to check. It verifies the expected paths.
Right.
But in a highly asynchronous distributed system where you have Alice's enclave, Bob's enclave, and the PBB all operating independently over unpredictable internet speeds, the number of possible event sequences is astronomical.
Yeah, you have race conditions, network dropouts.
Out-of-order message delivery, malicious tampering. A human programmer cannot possibly imagine, let alone write a test for every single sequence of events.
So if you can't write a test for every path, what does the EPN model checker actually do?
The researchers first took the entire logic of the FUWD protocol and abstracted it into finite state machines, pure mathematical models of computation. They then translated those FSMs into a highly specialized verification language called Promula.
How is Promula different from the Python code they use to build the actual app?
Python is an execution language. It tells the computer what to do step by step. Promula is a modeling language. It doesn't execute a program. Rather, it defines a map of every possible state the system could ever exist in and the rules for transitioning between those states.
Like a massive flowchart.
Exactly. Once they built the Promula model, they fed it into the SPIN model checker. SPIN is a mathematical engine that traverses that map. It doesn't run tests. It mathematically generates and systematically explores every single possible sequence of events that could ever occur within the defined rules of the system.
Wait, it explores every single possible permutation.
Yes.
If you have multiple independent variables moving asynchronously, wouldn't that state space be billions of possibilities? Doesn't that require a supercomputer running for months?
That is the power of modern formal verification tools like SPIN. They use advanced algorithms to collapse redundant states and optimize the search. The researchers note in the paper that running the SPIN verification for this protocol took only 1 to 2 seconds on a standard quad-core machine. It's just 2 seconds. But in those 2 seconds, it explores the entire state space. It looks for deadlocks, situations where the protocol freezes and cannot proceed, and it looks for infinite loops.
Okay, so Espinal proves the system won't crash or get stuck. But how does it prove the system is actually fair? How does it prove Alice can't cheat Bob?
To check for fairness, the researchers use something called linear temporal logic, or LTL formulas.
LTL formulas, okay.
They wrote mathematical statements about how the system should behave over time and asked Espinal to verify if those statements hold true across every single permutation.
Give me an example of an LTL formula. Just translate the math into plain English for the listener.
Sure. A core LTL formula they used essentially translates to: check every single path in the universe of this model. If there is a path where Alice eventually reaches the state of success, does Bob also eventually reach the state of success?
Okay.
Another formula checked the cancellation property. If Alice eventually reaches the state of canceled, does Bob also eventually reach the state of canceled?
And what happens when SpinPerfin runs these LTL formulas against the Promula model? What comes out?
It generates output files called .trail files. A trail file is a microscopic, step-by-step recording of exactly how the system arrived at a specific outcome. The researchers ran these verifications, and what they proved with absolute mathematical certainty is that in every single one of those millions of possible permutations, the internal variables representing success always matched.
Wow.
The variables Ali Sook and Bob suck. If Alice's variable registered a 1, Bob's registered a 1. If Alice's registered a 0, Bob's registered a 0.
Meaning there was not a single path, not one bizarre combination of network drops and database lags, where Alice succeeded and Bob failed.
Exactly 0 paths. The math proves that an asymmetric outcome is impossible.
That is incredible. So they didn't just build an app. They built a mathematical fortress, proved the fortress was impenetrable using temporal logic, and then they built the physical application based on that proven math.
That's the right way to build high-stakes software.
And you mentioned earlier they built the real-world version using Python and Docker. Does that mean this isn't just an academic exercise? Is this ready to be deployed by developers today?
It is highly practical. The researchers containerized the entire architecture using Docker. They created an Appia container for Alice, an Appia container for Bob, and a PBB server container.
So it's basically plug and play.
Yes. These containers run independently, communicating with PostgreSQL databases via RESTful APIs over encrypted TLS channels. By using standard open-source technologies like Python, Flask, and Docker, they proved that this unbreakable protocol can be deployed on standard commercial hardware right now.
Which brings us to the most exciting part of this deep dive, really, the real-world implications. We have this unbreakable, totally private, mathematically verified protocol. It removes the need for a corporate middleman who's actually going to use it. Because the paper links this technology to some really fascinating sociological concepts. It mentions socio-technical systems theory and Swift trust theory. What exactly is Swift trust?
So, Swift trust theory is a sociological concept originally used to explain how temporary high-stakes teams manage to work together effectively.
Like what kind of teams?
Think of a specialized surgical team, a film crew, or an emergency response unit. They have to trust each other instantly, despite having 0 shared history or prior relationship.
Right. The surgeon doesn't have time to bond with the anesthesiologist. They just have to work.
Exactly. In the physical world, Swift trust is based on roles and institutional backing. You trust the scrubs, you trust the hospital. But in the digital world, we constantly need to interact with anonymous entities we have no history with, and we lack those institutional cues.
Right. If I am interacting with a supplier in another hemisphere, I don't know their reputation. I can't look them in the eye.
The paper argues that protocols like FUWD act as a socio-technical bridge. They create swift trust mathematically. They allow complex, high-stakes digital interactions to happen instantly without waiting for traditional human trust to build over time, and without waiting for lawyers to draft massive contracts to artificially enforce that trust.
If you are listening to this and you work in the corporate world, think about how much friction, how much delay exists in business today simply because of a lack of trust.
It's massive.
You have compliance officers, you have escrow accounts, you have legal teams reviewing non-disclosure agreements for weeks just to set up a basic file transfer. This protocol acts like a digital trust bridge you could deploy in milliseconds. The paper gives a couple of really vivid, granular examples of where this completely changes the game. Let's look at the public health scenario first.
This is a scenario where the friction of traditional trust can literally cost lives. Imagine 2 major medical research hospitals, Hospital A in Europe and Hospital B in the United States.
Right.
A new, highly contagious, unknown pathogen has just started spreading. The researchers at both hospitals urgently need to cross-reference their patient data to track the vectors and identify the genetic markers of the pathogen.
But medical data is the most highly regulated data on Earth. They can't just attach an Excel spreadsheet of patient records to an email and send it over.
Absolutely not.
And they certainly can't upload all their sensitive patient data to some centralized third-party government server.
No, the legal frameworks like GDPR in Europe and HIPAA in the US strictly prohibit it. In a traditional setup to share that data, the legal teams from both hospitals would have to negotiate a massive bespoke data sharing agreement.
Which takes forever.
They would have to set up a legally recognized trusted third party, audit the cybersecurity of that third party, establish liability. That bureaucratic process would take months. Meanwhile, the pathogen is spreading globally.
But with the FUWD protocol.
With FUWD, Hospital A and Hospital B can execute a perfectly fair, perfectly private exchange of the data instantly.
Just vault to vault.
They define the data parameters, deposit the encrypted databases into the isolated keys on their respective local servers, and synchronize via the PBB. The data never leaves their secure enclaves, never touches a middleman, and is only unlocked at the exact moment both parties have irrevocably committed to the trade.
Wow.
It removes the bureaucratic friction from emergency response while maintaining absolute regulatory privacy.
That is powerful. It bypasses the lawyers without breaking the law. And the paper also brings up digital supply chains, which I imagine operates on a similar principle, but driven by intense corporate paranoia and the fear of intellectual property theft.
Precisely. The concept of information asymmetry absolutely plagues supply chains. Imagine a massive tech conglomerate company A needs to source a highly specialized next-generation microchip from a new supplier, supplier B.
Yeah. Okay.
To even give a quote, supplier B needs to see company A's most secretive proprietary technical schematics. But supplier B says, look, we won't even look at your schematics or dedicate our engineering time unless you sign this binding contract and send us a substantial digital down payment.
So it is the standoff all over again. Company A refuses to expose their trade secrets if supplier B might just steal the schematics and sell them to a competitor. Supplier B refuses to waste their time unless Company A puts skin in the game,
Right. And in the old world, they'd hire an expensive escrow agent.
which introduces delays and costs.
By utilizing the FUWD protocol, they completely eliminate the information asymmetry. Company A deposits the proprietary schematics into supplier B's hardware enclave.
And supplier B deposits the signed digital contract and the payment token into Company A's enclave.
Exactly. They verify the files mathematically inside the enclaves, they post their synchronization tokens to the public flagpole, and the exchange happens simultaneously. No corporate espionage, no opportunistic behavior, no escrow fees.
It creates a completely frictionless, zero-trust digital ecosystem.
It does.
And because the protocol is application agnostic, you can start to extrapolate how this could be integrated everywhere. We could see this architecture powering complex smart contracts on blockchains, making decentralized finance incredibly secure. It could make high-value e-commerce completely dispute-free. Imagine buying a highly valuable digital asset-like enterprise software or exclusive media rights, and knowing with absolute mathematical certainty that the millisecond your payment clears, the file is yours. You don't have to trust the vendor at all. It entirely removes human mediation and human error from complex digital deals.
It represents a fundamental structural change to digital governance. For 20 years, we have centralized our trust into massive, vulnerable institutions,
The honeypots.
the honeypots. By moving the trust mechanism from those central servers into verifiable code running inside isolated hardware on our own local devices, we distribute power back to the edges of the network. We make the global system fundamentally more resilient, more efficient, and infinitely more private.
Let's bring this all together. What an incredibly dense, intellectually satisfying journey we have been on today. We started by looking at the mathematical traps set by Panya and Gartner in 1999, the proof that you must have a middleman to achieve fairness.
A requirement that seemed to doom our digital privacy forever.
But the FUWD protocol breaks out of that trap. It takes that monolithic, vulnerable middleman and chops it into three pieces. It leverages the isolated cryptographic hardware vaults that already exist inside our laptops and smartphones, allowing us to lock up our sensitive data locally.
Right.
And then it uses this beautifully simple, stateless public bulletin board, just a digital flagpole logging text strings, to coordinate the exact simultaneous moment of the trade. And the researchers didn't just build an app. They used Promula and Spanion model checking to mathematically explore millions of possible futures, proving with absolute certainty that nobody can be ripped off.
It is a phenomenal piece of software engineering and theoretical computer science. The seamless combination of rigorous mathematical verification and highly practical, deployable implementation is what makes this 2026 research so compelling.
It really is a masterpiece of system architecture.
It takes a vulnerability that has plagued distributed systems for decades and provides a robust solution that is ready for the real world today.
And looking at how perfectly it functions, it leaves me with one final, slightly provocative thought to chew on.
Oh, it's here.
Throughout all of human history, the concept of trust has been the fundamental glue of society. We build relationships, we protect our reputations, we shake hands, we look people in the eye.
Very true.
Trust is an emotion,
Yeah.
right? It is a social bond built over time. But if protocols like FUWD become the underlying standard of our digital lives, if we can mathematically guarantee perfect fairness and absolute privacy without any human oversight, what happens to the human element of commerce and interaction?
That's a deep question.
Right. If we no longer need to trust the people we interact with because the code guarantees our safety, will the very concept of trust become an obsolete emotion in the digital age? Will future generations look back at the idea of taking a leap of faith, not as a virtue, but simply as a primitive security flaw that we eventually patched out of existence? Hey, about that next time you find yourself in a digital standoff, your finger hovering over the keyboard, wondering who is going to hit send first. Thank you for joining us on this deep dive. Keep questioning the hidden architecture of the digital world around you. We'll see you next time.